thanks everybody for coming out tonight. I have to say it's a little weird to be on the other side of this. I'm used to being in the audience and now standing up here and yikes, wow, I guess I'm a grown-up and a scientist now. It's kind of surprising sometimes, but anyway, I'm excited to come talk to you today. I study asteroids, like Bob said, asteroids and comets, and I do computer models of them and how to make them not hit the Earth and what happens when they do hit the Earth or other planets, and I'm going to tell you a little bit about that tonight. So first, a show of hands. How many people have seen a shooting star before? Pretty much everybody. That's awesome. All right. Has anybody seen a comet before? Yeah, I know most of you older folks have seen the ones that came through in the 90s. We haven't had too many in a long, long time. But we do have a comet that's coming up. It's going to be Comet Pan-STARRS, and that's going to be coming by next month. So that's going to be pretty exciting. Unfortunately, it won't be one that you can see without binoculars, but if you've got a pair of like birdwatching binoculars, something like that, you'll be able to look up the coordinates for it on the internet and find it with your binoculars and see a comet. So that is one of the many exciting things that come shooting past our planet. So this is our really, really busy solar system. And let's see if I've totally got a laser pointer here. So you are right there. So these pictures are zooming out. If we start outside the solar system, looking in like we were space aliens on a spaceship, this is the Oort Cloud. It's a cloud of comets that surrounds us like a bubble. And it goes out much, much, much farther than the rest of our solar system. If you were hanging out in the Oort cloud, the sun would look like a flashlight. It's so far away. And so this is full of billions of comets that are just floating out there in deep space where it's really cold. And every once in a while, one of them will get shoved by a supernova or a little bit off balance by some sort of gravitational interaction with a passing star, and it'll fall into the inner solar system. And as it's coming into the inner solar system, the next thing it does is go through the Kuiper Belt, which was discovered here in New Mexico, and passes the planet, the dwarf planet now, dwarf planet Pluto. It's not a full-on planet anymore. We call it a dwarf planet because it's not quite the same process that made it as the other planets. So Pluto's big enough that it has enough mass that the gravitational attraction of all that mass pulls it into a sphere. But it didn't go through a lot of the same melting and what we call differentiation processes that all of the other planets went through. So it's not quite the same. It didn't finish baking, sort of. So as we zoom in, we go past Uranus and Neptune and Saturn and Jupiter, and then we're into the inner solar system here. This outer circle is the orbit of Jupiter, which is the biggest planet in the solar system. And it's so big that it has two groups of asteroids that orbit with it in its orbit, one going in front of it, the Trojans, one going behind it, the Greeks. So those are two sets of asteroids that orbit with Jupiter. So what we've got here is asteroids and comets are sort of the leftovers of the formation of the solar system. We started out with the solar nebula that condensed down, became the sun at the center, and then a cloud of matter around it that collapsed and collapsed and condensed and condensed. And the first things to freeze out of the solar nebula were out in the outer solar system in the Oort cloud and the Kuiper Belt, and where the gas giants are were things like water, ammonia, things that freeze out at lower temperatures. As you go into the inner solar system, when it was still forming, it was still really hot. So things with higher melting points like iron, silicon, rocks, those were the things that were condensing in the inner solar system where the sun was still heating it up. So that's why we have icy things like comets in the outer solar system, and we have rocky things, the planets and the asteroids in the inner solar system. So inside of the orbit of Jupiter, we have the asteroid belt. The asteroid belt is where most of the rocky and metallic asteroids in the solar system hang out. And this was a planet that didn't quite make it. So it's about the same amount of mass as in the planet Mars. But for some reason, as all of these bits of rock were condensing out and sticking together and making bigger chunks and bigger chunks and bigger chunks, for Mars and for us on the Earth and for Venus and Mercury, those chunks got big enough that they became full-size planets. But for some reason, and we don't completely understand it yet why, the asteroid belt didn't become a full-on planet. So it got to chunks that were certain sizes, but then those big chunks, we call them planetesimals, started bashing into each other and grinding each other back apart again. So instead of having an extra planet right there, we have the asteroid belt. Inside of the asteroid belt, there's still a pretty crowded field there. We've got Mars, we've got Earth, Venus, Mercury, the Sun at the center, and all through there we have asteroids that we call near-Earth or Mars crosser, Venus crosser, Mercury crossing asteroids that are swarming all through the inner solar system with us. So here's a zoom in on a comet. Comets are basically dirty snowballs, so they're mostly different kinds of ices: dry ice, carbon dioxide ice, methane, ammonia, water ice, and little chunks of dust that go up to be about, the biggest ones are about the size of your thumbnail. So this is pretty powdery stuff that's mixed in with the ice. And that's what we see as a comet's tail. When a comet falls into the inner solar system, then that ice vaporizes off and flows behind the comet in the solar wind, which is coming off of the sun, and blows it back, and that's what we see as the comet's tail, with the little chunks of dust mixed in. Asteroids are big rock piles, big gravel piles. They're made of boulders, they're made of sand, sometimes they have pieces of metal in them. So I actually have a piece of a meteorite up here that I can show you afterwards. I'm not going to pass it around because there's too many people, but if you want to come see it, come check it out. And so we have all different sizes of asteroids here. Let's see, we've got, which one have we got? We've got, for perspective, here's Comet Halley down in the corner, just to give you some sizes. This big one here is asteroid Lutetia. If you follow NASA and ESA space missions, you might have heard of asteroid Lutetia. This is one that just got close approach by a satellite that orbited and took a lot of pictures really close up. So we got to see a lot of detail on the craters and the gravel piles and the boulders that are all over this thing. And so we're learning a lot from that. This is asteroid Eros, which was the focus of the NEAR mission back in the 90s. We actually landed a spacecraft on that one. This is asteroid Itokawa, which you can't really see. It's sort of peanut-shaped when you zoom in on it, but that one was visited by the Japanese spacecraft Hayabusa back in 2005. And that one is important because we have the first return of a sample from an asteroid, from asteroid Itokawa. So something that we learned from asteroid Eros and from Itokawa, which were the first two space missions to asteroids, was we learned that asteroids are not solid when they're big. So when asteroids are little, say about the size of this building, we can tell that they're usually solid because they spin really fast. And you know if something spins really fast, like if you're holding a bunch of marbles in your hand and you spin around, they're going to fly out of your hand. That's why I had to hold onto the clicker instead of letting it go. So we see them spinning so fast that we know that if they had boulders on them or gravel, that would just fly right off. So those have to be solid when they're little. But the bigger ones, like the size of Itokawa, which is about half a mile across, or a quarter mile across, asteroid Eros, which is actually on its long axis, it's about 15 miles across, those are big gravel piles. And there's nothing underneath. It's gravel all the way down. And so when they spin, they become these really interesting sort of potato shapes. And they get hit by different asteroids, and pieces will spray off and then come back together in different shapes. It's really interesting, and it's all dominated by gravity. So these things are really complicated, really interesting objects, and they're also very, very delicate. So it turns out that sometimes these things hit each other, and sometimes they hit planets like Earth. So here's a map of most of the impact craters on Earth. We're actually missing one in Russia because this is an older map now, but we'll talk about that one in a little bit. So if you look at this map, what sort of patterns do you see here? Anybody see a pattern? You see a pattern? What pattern? The populated areas, yeah. We've got the US here with a bunch. Australia's seeing a lot of love down there. Europe. So what do you think they have in common? Population is a good idea. That's something we got to watch. But these are impacts that some of them happened millions and millions of years ago, so there weren't people living there yet. But this is just over time. These have accumulated impact after impact after impact. What other patterns do you see? Is there something maybe with the rock that maybe might cause it to have more impact craters? Anybody? Let's see. So what do we know about the water? There's no impacts in the water so much because they've, huh? There's some that are closer to water, but you notice in the oceans we don't have very many craters. There's a reason for that. Oceanic crust is very, very young. So in the Atlantic Ocean here, we've got the Mid-Atlantic Trench that's spreading apart. It goes up onto Iceland, and you can see the lava fountains there sometimes in Iceland where the crust is spreading apart and you're making new crust all the time. You've got Hawaii over here with volcanoes spitting out lava all the time. So oceanic crust is the youngest rocks on Earth. Those are the young rocks. On the continents, that's where stuff tends to pile up and get stuck. And it floats, the granite floats a little bit over the basalt. And so things pile up and you get older rocks on the continents. So can anybody maybe tell me where do you think the oldest rocks are? Any votes for Australia? Any votes maybe for up here in Scandinavia? All right, yeah. So what's happening here is the longer a continent or an area of rock is hanging out on the surface of the Earth, the more time it has to get hit. And so the more impact craters we find there. So point of interest, there's Meteor Crater in Arizona, and there's a dot right there next to it. Guess where that is? That's right out here outside of Santa Fe. There's an impact crater that we didn't even know about until some geologists in the University of New Mexico were going up there. And I have to say, I'd been driving past this little road cut to go skiing for years, never saw a thing. But the right geologist was up there at the right time and recognized the signs in the rocks that said, hey, this was underneath an impact at one time. Now the crater's all gone. It doesn't look like Meteor Crater anymore. But if you know what you're looking for, you can still see it. It's just out past 10,000 waves on the way up to Hyde Park. So here's Meteor Crater in Arizona. This is one of the freshest craters we have. The asteroid that made this one was about 50 meters across, or 50 yards, so about half a football field. And it's now a very big crater. This is about, I want to say, a mile across-ish. So it's a really interesting one if you ever get a chance to visit it. It's a lot of fun, and it gives you a very good idea of what these things look like.
How old is that?
Meteor Crater is about 100,000 years old. So there weren't people living there at the time, but there would have been a lot of sort of Ice Age animals running around. So it was an exciting time in Arizona. So craters like that are one of the things that I model. So I use big supercomputer systems to model what happens when one of those things hit the ground. And a lot of other people do that too. And one thing we've found is when one of these hits the Earth, it's got a whole lot of energy in it. So you remember the one that hit Russia that I'm sure you've all seen on YouTube? That one was a lot smaller than Meteor Crater. And it was still big enough to shatter everybody's windows. When something like Meteor Crater happens, if that hit in modern times, that would have taken out the town of Flagstaff. It would have been a really big deal. The blast would have destroyed buildings. So these things are really, really important events. They don't happen very often, but when they do, they're very powerful. And so they're something that scientists like to study, just to keep an eye on. So how often do impacts like this happen? I just said they don't happen too often, fortunately. So let's see, we have the Cretaceous Paleogene. We've just changed the name of that that geological layer, but it used to be Cretaceous Tertiary, now it's Cretaceous Paleogene event. That's the one that killed the dinosaurs that hit down in the Yucatan. That one, when it hit, it was so big that when the front leading edge of that asteroid hit the surface of the ocean, the back end of it was still 5 miles up in space. It was absolutely huge. The earthquake that it made was a magnitude 12 earthquake. Now, the Richter scale only goes up to magnitude 10. They had to add another multiple of 10 and another multiple of 10 to it to get how big that impact or that earthquake would have been. The tsunami that it raised went all the way into Texas. It was absolutely amazing. It blacked out the sun for probably 6 months over the entire globe. Debris that was ejected from that impact went all out into space and rained back down all over the Earth, lit off forest fires all over the world. It was a complete mess. So we don't want to see another one of those. The Tunguska asteroid on the other end was about 2, maybe 3 times the size of the one that hit Russia a couple of weeks ago. It also hit in Russia. It hit in Siberia in 1908. And until Chelyabinsk, it was the biggest that we had had in recorded history that we had atmospheric data for, that we had studied. So that one would have been about the size of the largest hydrogen bomb ever detonated. It would have been about 500 megatons in impact energy and blast energy. Fortunately, at the time in Siberia, nobody was living nearby, and so a couple of people got knocked down by the blast wave, but nobody was killed, didn't even bust any windows, just knocked down a bunch of trees. Interestingly enough, Tunguska, even though it was bigger than Chelyabinsk, we never found a crater. We never found any of the meteorites. There are no Tunguska meteorites. There are little bits and pieces that have been found embedded in wood from the trees that were knocked down by the blast, but we've never found any larger pieces than maybe the size of a piece of dust. So there was another really exciting one in 1994. This was a tiny, relatively air blast that hit. It was about the size of the Hiroshima bomb, so it was enough to get people's attention and trigger the meteorological satellites that look for this stuff. The bummer with this one, with Kusai, was that it hit over the Mediterranean in such a way that if it had hit about 20 minutes earlier, it would have hit into the Kashmir region between India and Pakistan during a nuclear standoff. The other trick with these things, you can't so much tell the difference between an asteroid impact and a nuclear bomb unless you got a Geiger counter. And if you've got an itchy trigger finger, you're probably not going to wait. So we keep a very close eye on these things for the little ones like that hit about every, say, 10 years. We have to keep an eye on them just for events like that so it doesn't get somebody nervous. Unfortunately, those are also really hard to find. That one would have been about 10 yards across. And we don't have telescopes that can see that so well right now, but we're trying. We're starting to get better at it. So preventing these impacts and finding them are really important. The first thing you have to do before you can prevent impacts like these is you have to see them. So we have a lot of telescopes now that are looking for these things. We have ground-based telescopes in Hawaii, in Chile, in Europe, in Australia, all over the world. We have telescopes that are looking for these, doing what we call all-sky surveys. So they take pictures of the entire sky every night, and then they compare them to last night's pictures and the night before to see what's changed. And when you're looking for asteroids, you're lucky if you see that. So you see a little streak that's going through your image, and that's how you know it's moved, but that's only if it's moving away from us or moving sideways to us. If it's moving at us, we might not see it move because there's no translational motion relative to the camera. It's just coming straight at you. So it might just look like a fixed star like the rest. So that's where we do the image differencing. So we have the all-sky surveys. We have radio telescopes. So if we have an object that's coming near us but not going to hit us, we can bounce radio waves off of it from the VLA or from Arecibo down in Puerto Rico, and we can get a shape model of it, and we can tell how big it is and what it looks like. And then we do follow-up observations at different telescopes all over the world whenever something's coming back so that we can get better parameters on the orbit so we can predict where it's going to be. And with these orbits, if we have enough data, we can actually predict where this asteroid is going to be for hundreds of years. And so NASA actually keeps a database at JPL for all of these objects and where they are and when they're coming past us again. It's actually really neat to look at. Another important part of the asteroid detection process is amateur astronomers. Amateur astronomers have found some very important comets. Amateur astronomers have found asteroids that are potentially hazardous. It's a big deal. It's something you can actually do right here in Santa Fe. If you have a small backyard telescope, you can actually do really good science and report these things to the International Astronomical Union. And if you find them, you get to name them. So it's kind of an exciting thing you get to do. And I would really encourage you guys, if you have, you get to name them. So it's kind of an exciting thing you get to do. And I would really encourage you guys, if you have a chance to get to try out a telescope at one of the astronomy nights that the local astronomy clubs do, go check it out, because it's pretty fun stuff. So this is what we get in terms of near-Earth asteroid discoveries. This is over the past couple of decades as we've brought the asteroid searches online. You'll notice it starts about 1995, after we all got good and nervous in 1994 with the one that snuck up on India and Pakistan. We started looking for these near-Earth objects about that time. Now, a near-Earth object is something that comes within a certain distance of the Earth's orbit. So when we're sitting on this planet, we feel like we're sitting still, right? We're actually hauling through space at 1 million miles a day. This planet is just shooting around the sun. And so these objects that we consider near Earth are things that come within about a week of missing us. So that's about 7 million miles. But a week's a pretty close shave. So you'll see that over time we're getting better telescopes. It's like getting new glasses. You know, all of a sudden, oh, those trees have leaves again. It's awesome. So we're now to the point where we're discovering about 1,000 of these objects a year. Unfortunately, one of our really good telescopes here, in orange, was Pan-STARRS. That was an infrared telescope, or I'm sorry, Pan-STARRS, no, that was, which one am I thinking of? I'm sorry, it wasn't Pan-STARRS, it was one of the other surveys that's not on here. Sorry, anyway, there was another survey that was done by Space Telescope, and that one's now finished. That would have, I guess, been in the all others, never mind. Pan-STARRS is a binocular telescope. That one's actually going to get better over time. They have 2 telescopes that are, I'd say the mirrors are maybe from me to the second row across. And they have 2 of those, and so they look in space and they can do a little bit of 2-dimensional stuff. They can get higher resolution from, or 3-dimensional rather, distance stuff. They can get higher resolution from having 2 telescopes. They're going to get a 3rd one coming online in a couple of years, and then they'll get really good resolution with their telescope and be able to see even more of these objects. So we're getting better at this over time. Back in 2003, the Spacewatch survey in red was able to announce that they had determined that there is nothing the size of the dinosaur killer impact coming at us. There are no more 10-meter objects or 10-kilometer objects coming at the Earth. So we're safe at least from that. Now, 1-kilometer objects will still mess up the whole Earth for quite a long time. It wouldn't kill everybody, but it would really ruin your day. So we're doing our best to find all of those. And once we've mapped out where all of the 1-kilometer, half-mile diameter objects are, then we can keep marching down. Now, we'll find smaller ones as we go, but it's important to find the bigger ones first, and they're also easier to find. So the Chelyabinsk Airburst, the one that happened a couple of weeks ago that was amazingly caught on video from so many different angles. So it happened at about 9:30 in the morning, local time. It exploded 3 times as it was coming into the atmosphere. So how many of you watched a video maybe online of the space shuttle when it was landing? Do you remember that? What happened when it was coming in? It was still really, really high up, but as it started coming in the atmosphere, what happened? It starts glowing, right? Why does it start glowing? Friction, good, yeah, the air, even though it's super, super thin air, it starts rubbing against the hull of the space shuttle and heats it up. Same thing happens to the asteroids, so that's why shooting stars glow, is that friction. So as it was coming in, it's heating up, and it's not that strong of an object. It's cracked all over the place where it's been beat up in space. So as it's heating up from the friction, parts of it start to melt on the outside. That melts, and rock vapor and iron vapor goes into those cracks and shatters it. So that happened 3 times as it was coming down. Boom, boom, boom. Now, those explosions blew it apart, but those were not what was felt on the ground. What was felt on the ground were actually sonic booms. So this thing, when it was coming down into the atmosphere faster than a fighter jet. It was coming in at 33,000 miles an hour. So it was the big sonic booms. When it hit a dense enough part of the air, it made that sonic boom, and that was the shock wave that then hurt everybody and shattered glass and caused about $33 million in damages. So if you ever wonder You know, why should we be putting tax money to funding all these crazy astronomers looking at the stars all night? Well, it's to find stuff like this before it hits. So again, it blew up 3 times as it was coming in. It shattered 3 times. It started out the size of a train car, about the size of one of the cars on the rail runner. It shattered, and the rocky material from the original object was dispersed all over the area. A lot of it has been found now, but the pieces are all pretty small. There's no big chunks yet. There may be one big chunk in a lake. There was a 25-foot hole in the ice on a nearby lake, and they think that down at the bottom of the lake there's probably a big chunk of this stuff. But a 25-foot hole is not big when you're starting out with a train car. So it was only a fraction of it that made it intact all the way to the ground, we think. But again, they haven't dug it out yet. So we'll find out. So again, I talked about that earlier impact 100 years ago that hit Siberia called Tunguska. So that was one that was really interesting. We were studying for a long time. We couldn't figure it out because we never found the meteorites, never found a crater. And then along comes Chelyabinsk. So we found out from Chelyabinsk that when we get to 20 meters, about 20 yards in size, that's where you need to start worrying about these things when they start hitting cities. Those hit every 50 to 100 years, it looks like, based on these 2 data points that we have of one that hit 100 years ago and one that hit now, and smaller ones that we know how often they hit. And so we know about how often it happens now. We now can tell, okay, something 20 meters, we got to start worrying about that because that's going to ruin people's days if it hits a big city. If something gets up to maybe 50 meters, that's about the size Tunguska would have been, then that you really have to worry about because that's not just going to ruin people's day, that's going to burn down your city. So we have to really watch for that. One of the most amazing things about Chelyabinsk was everyone had their dashboard cams and their smartphones and their webcams, and they were all filming it. So I felt really bad for everybody getting hurt, but I totally would have been there doing the same thing. Because when you see one of these things coming down, you can't tell how far away it is, and you can't tell how big it is. So you don't know if it's maybe a 1-meter thing that's just going to make a big boom, and you're not going to have to worry about it, or if it's 20 meters and you need to be ducking and covering. You don't know that. So we had all of this amazing footage that people got, and it helped us constrain our models for these earlier impacts like Tunguska. So the next question is, all right, we've studied these things, we know about them now, we can start to predict how often they happen, how big they are, we're starting to find them. Now when we find them, what do we do about it? There's basically 2 choices. You can either disrupt and disperse the object, or you can try and push it out of the way, off of its orbit. So disrupt and disperse tends to be done or want to be done for 2 reasons. Either it's coming in really soon and we just discovered it and we've only got 6 months, so we got to get it out of the way and we don't have a lot of time to react, so we just want to get rid of it. Or it's something that's too big to push out of the way. So something that is maybe half a mile across, we can't do some of these gentle nudges. It just doesn't work so well. So there's a lot of debate still going on with different scientists about how this works and when you do one, when you do the other. But this is the basic idea. So there's a couple different ways you can do the disrupt and disperse. Basically, the idea is to blow it up into fragments that are small enough that if any one of them hits the Earth, you're not going to get anything bigger than a Chelyabinsk. So you can have people duck and cover, and it'll be OK. So you can use kinetic impactors like cannonballs, basically. You can use explosives like nuclear devices, potentially. Or you can go grind it up with an asteroid mining company and bring it home for pop cans. That works with smaller ones, not so much with bigger ones. This works best, again, for smaller objects or for short warning times. The other more graceful one is what we call deflection, or pushing it off its orbit. So if here's the sun, here's the Earth on its orbit, and you've got an asteroid that's coming in on a parabolic or an elliptical orbit, something that's kind of funky, but it's going to cross us. The idea is if you can catch it earlier in its orbit, so when it's out here instead of right there, if you can catch it way out here, maybe 50, 100, 200 years early, then you can go to where it is, and you can push on it to slow it down or speed it up. So if Earth is moving this way in its orbit, and you've slowed the object down, so it's on this, almost the same trajectory. But if you've slowed it down, then Earth will come through, and then it'll pass and miss us. Or if you've sped it up, oh, it'll fall in a little before we get there. And so the main idea is just make it be there when we're not. And so there's a lot of different ways that are being talked about to do this. Some using lasers to heat up material and vaporize it off the surface and make the asteroid or the comet into a little bit of a rocket and push it away. Potentially solar sails, if you know that from science fiction, big mylar sheets that drag on it like a sail on a sailboat, only you're using the wind off the sun, the solar wind, hydrogen ions coming off the sun. There's one fun proposal called a glitter bomb, where you take metal flakes, coat the asteroid with that so it's shiny, and then light pressure knocks it off of its orbit. There's all kinds of interesting ways you can do this. These work best when you have reaction time in the decade to century range. So it takes a really long time for these very delicate processes to work. The nice thing is they don't disrupt your asteroid, so you don't have to keep track of the bits afterwards. They just push it off. But a lot of these things are also technologies that are very much still on the drawing board. So we think we can make it work. If we have a lot of warning time, we'll have plenty of time for the engineers to think about it, but we'll see. So the big physics question here, that it's the root of the whole impact prevention thing, is momentum. So momentum is a measure of mass in motion. That'll help you on your next physics test, I hope. So the question is, how much stuff do you have, how much mass? How fast is it going? And that quantifies momentum. There's an equation in there somewhere, but I'll leave that for your physics teacher. Don't want to spoil it. So deflection works by transferring the momentum. Deflection is pushing it out of the way. Works by transferring the momentum to the asteroid or to the comet. You either push on it or you knock mass off. And that changes the momentum by either changing the speed it was going or by changing the mass that it is. So that changes its orbit. So here's a deflection idea that's pretty cool. This is called a gravity tractor. This is totally Star Trek. This one is a design for a giant spacecraft with very, very precise engines. So what you would do is you'd have a whole bunch of mass on one side of it, and then you would have these very precise engines that would be able to navigate very, very carefully. And then you take this thing and you park it right off the side of your asteroid. And just like holding out a carrot for a donkey, the donkey's going to come over and want to see that carrot, and then you step a little out of the way, and the donkey's going to follow you. And you step a little out of the way, and the donkey's going to follow you a little more, and then you move your donkey. Same thing with the asteroid. The asteroid, because it's a big mass, is attracted to the mass in your gravity tractor, and the gravity just pulls it along. And this would be just millimeter by millimeter by millimeter. This would take a very long time to work, but it has the advantage of doing so in a way that's very careful. So when you have these big comets and asteroids that are more delicate than freshly fallen snow, it doesn't rip it apart. Here's a solar sail. Again, for smaller ones, you can put these big mylar sheets out, potentially, and push it out of the way. Solar sails have actually been deployed in space for payloads about the size of a coffee can. So we're still working on it, but at least they've flown. And then another deflection idea that I've worked on is nuclear devices. So this is one that comes up a lot with the governments around the world. They say, oh, well, if we've got something coming at us, just like in Hollywood with Bruce Willis, we'll just nuke it, push it out of the way. The problem is we don't completely understand how a nuclear device is going to affect a comet or an asteroid, and so we need to very carefully do the math before we start saying, oh yeah, it'll work. So that's what I do. I use computer programs at Los Alamos to model exactly what would happen when you have that kind of energy deposited into that kind of rock. So to step back and get philosophical really quickly, so this is one of my favorite cartoons. And at the top, you see pretty little scene. You got a stream, you got a bunny. And then down here, this is how I see the world. It's all math. So you've got the sun up here, and you've got fusion going on, and it's burning the hydrogen to helium, and all these things going on. And then these equations here are how light works. And then you've got pieces of the solar wind are hitting here, and you've got quantum mechanics going on in the upper atmosphere. So those particles fall down and become other particles and do cool things and stream through us, and we don't even notice. And then you've got trees here doing photosynthesis, and you've got your bunny rabbit who's breathing and eating. And you've got your stream that's flowing according to stream equations, that fluid flow equations that we know. So all of this stuff we can model in math. And so I take all of these equations And I make computer models of them because solving them by hand really is a drag. So you put them on the computer, and you can do a lot more with them. And so that's what this is here. This is a mesh from a program where I have taken equations for fluid motion, because when you punch a rock hard enough, it's going to act like a fluid. And I have taken equations for light and equations for heat and equations that tell me how rock acts when you heat it up or when you squish it. And I put all of those equations together into this program, and then I set up the model and let it run, and then it tells me, okay, if you've got this much light flowing from your nuclear device up here onto your nice round rocky asteroid there, then what's it going to do? Is it going to heat up? Is it going to vaporize? Is it going to blow something off? And that's what I get here is this part is hot as the light has radiated out away from the point where it started. And then there's vapor coming off there as well. That intersects my asteroid, heats it up, and then this here looks like hair, but it's actually arrows whose length tell me how fast the rock from the surface is blowing off. And if I know how fast that material is blowing off and how much, mass in motion, I know momentum transfer to the asteroid. If I know momentum transfer to the asteroid, I know how it's being pushed away and how its orbit will change. So that's what I do. And again, here's another deflection idea. This is the glitter bomb. The idea is to paint the asteroid, make it shiny, and then it will spin in a little bit different way than it's used to, and that knocks it off of its orbit. And so it's being tested in some ways. There's a gotcha with this one, though, in that we discovered during the asteroid, or the Apollo program, that in a vacuum, dust will actually get static charge and hover. And so what we're worried about with this one is, yeah, it could work a little bit, but the problem is the asteroid dust is going to hover and cover your paint again, so you have to keep painting it, like Tom Sawyer painting his fence. You got to keep going. So it's out there to be tested, but I'm pretty skeptical personally. There are a lot of technical limitations again with this. So launch capabilities. We can only launch so much mass into space at once, and we can only launch rockets so often. Delta V is change in velocity, how much your rocket can push you. That tells you how far away you can get and how fast. Operating in low gravity on an asteroid, they're big rocks, but they're not that big in terms of gravity, and so you dock with them, you don't land on them. And so it's like operating on the space station, where you don't notice the gravity. And so it's very complicated to interact with something like that that's a very delicate object that's in low gravity. It's hard to dock to it, it's hard to attach things to it. And then remote observation of what's going on is also complicated, involves a lot of telescopes, and it's rocket science. So again, to wrap up, the science questions that we have for preventing asteroids and comets from hitting the Earth is momentum transfer, which involves a couple of different mechanisms, either changing the velocity, changing the mass. If your asteroid is tumbling, that could get complicated because then you're not pushing it in one direction, you're pushing it in a bunch. The physical properties of the object, is it ice? Is it metal? Is it solid? Is it a gravel pile? Makes it complicated. Standoff distance, trying to figure out what's the optimal standoff distance for a nuclear blast, or the optimal mass for a cannonball, or the optimal shininess for the paint, gets complicated. This means you need a lot of lead time. We may have 200 years, we may have 6 months. It really depends on the object. And it really depends, again, on the specific object properties, its size, its velocity, its orbit, how delicate it is, as to whether you want to do one mitigation method versus another. But it's a really fun problem. It's a really complicated problem when you're dealing with objects like this. This is Comet Wilt 2, which was 2 miles across and was visited by NASA spacecraft back in 2005, I believe, the Stardust mission got there. And so it was big. It's solid because comets tend to be more solid, asteroids tend to be rock piles, but it's a very delicate solid. Comets are more delicate than freshly fallen snow. If you tried to poke at it, your finger would go straight through. It's kind of amazing. But when they come at us, they're going faster than fighter jets. And this one is bigger than the Plaza. So it's a really complicated, really interesting, beautiful object. And I think I'll wrap it up there and take questions. So.
We have time for questions and discussion. I hope you'll do that. And let me just urge you to fill out your form. And then at the end of that, I'll call out a number. There's a number on the top right. And the person who has the number will be the winner of the tickets. So let me ask a question.
Yeah.
So could you orient us by telling us how big the comet was that is responsible for the extinction of the dinosaurs?
That one was not a comet, actually. That was an asteroid.
Okay.
So we've figured out from samples of it as to what it was made of, and then we can tell from that which asteroid family it came from. And there was actually a scientist up in Colorado that suggested it comes from the Baptistina asteroid family. And so let's see, you were asking again how big it was?
Yeah, I mean, compared to the ones you were talking about.
Compared to the ones I was talking about, it's bigger. So that one was 5 miles in diameter, and the ones we're worried about, so the one that hit Chelyabinsk was maybe like 15 yards diameter, at most 10, 15 yards, so big difference.
Was that a meteor or an asteroid?
Chelyabinsk was a meteor. It was, so when it's in space, it's called an asteroid. When it's going through the atmosphere and it's all glowing and blowing up, then it's a meteor. When it hits the ground, it's a meteorite. So if you want to come up afterwards and see this meteorite, this is a stony iron meteorite, and it's the same kind that hit Chelyabinsk. So you can see, when you look at it, you'll see that it's actually a bunch of little different pieces that are all sort of melted together. And some of it's iron, some of it's silicate, some of it's calcium. It's really an interesting little object, so please come take a look. Yes?
What do we know about the composition of the Tunguska object?
Not a lot.
Say some of the questions.
Okay, yes, I'll repeat that back, I'm sorry. So what do we know about the composition of the Tunguska object? So it was suggested, because we never saw a crater and we never recovered a meteorite, Carl Sagan, who was an astronomer who was very famous in the 70s and 80s, suggested, oh, well, maybe it was a comet. Maybe there was nothing left to make a crater because it melted on the way down. And so that was the reigning hypothesis for a while. And then about 10, 15 years ago, we realized, well, wait a minute, comets don't hit us that often. And other things that we do know about that are carbonaceous chondrites, which are sort of crumbly coal-looking things, or these stony irons, they hit us a lot more often. So if Tunguska was a comet, then we should be seeing a lot more of these other objects hitting us, and we should have meteorites from that, and we don't. So that actually ruled out the comet hypothesis. And now the reigning hypothesis is that it was a very crumbly, probably a carbonaceous chondrite, because we don't have a lot of material from it to go on. We see a few things like I said, embedded in the trees, but it's kind of maybe. But yeah, the jury's still out. But we think it's a carbonaceous chondrite. Yes, sir.
Isn't there supposed to be an apartment-sized comet hitting the Earth in 2036?
In 2036, there is not supposed to be an apartment-sized comet hitting in 2036. The one that's going to approach us in 2036 is called asteroid Apophis. So it is about 250 meters across. It actually came by us just this last winter on a close approach. And so we have now radar bounce data, so we have a shape model for it. We know what it's made of. It's another one of these rocky, kind of iron, kind of rock ones. It's made of a bunch of big boulders. It's not solid, but it's not a sand pile, which makes it a little more interesting. We think it might hit in 2036. It might hit Russia. It's a pretty low probability, so it's always a gamble with these things. It's always chance. It's always probability. It might hit here with this probability, or it might miss us completely. And it's a pretty low probability. You're more likely to get hit by a car than get hit by this asteroid. By a long shot. You're more likely to get eaten by a shark, actually. So with this one, because it's looking like it might hit Russia, the Russians are really interested in it, and they should be, because if it's going to hit Russia, it's going to hit in a bunch of their farmland. So they're worried about it, and there are a lot of people in Russia that are doing the sorts of calculations like I just showed you that I did for that one to try and see what they should do. Now, personally, I don't think it's going to hit. So I actually have a bet running with one of my friends in Russia that in 2036, if we're both still around, we're going to go sit in the middle of the impact zone there, and we're going to go sit and have dinner, and we're going to put down our credit cards, have a really big dinner. Now, if the thing hits, I'll pick up the tab. Because I won't be there to pick up the tab. Next question. Any kid questions before we go to the grown-up questions? All right. Kid question.
Why are so many comets hitting Russia?
Good question. Do you have any hypotheses for why that should be? Do you have a hypothesis?
Not really.
No? Does anybody have a hypothesis? Why is Russia getting beat up? Because it's big. Russia is the country with the largest land mass of any of the countries. So the more land you have, the more target you got, the more you're going to get hit. So that's why. Let's see. Yes, sir.
I noticed in the map of impact craters, you don't see too many in upper South America in that region. Is that just because it's so forested?
No, these things, those impacts that it's not because we don't see them necessarily. So all of those impacts, the dots that I used were the same size, but some of those are tiny impacts, some of them were huge. So the reason we don't see very many down in that part of South America is because that's where the Andes are. So that's really young rock. Those, it's been heaved up, it's been changed, it's been pushed up, it's messed up, so we don't, if they hit, we don't see them, but mostly just the rock hasn't been there long enough. And you, sir.
The 2-mile asteroid, how far is it in the location?
Pardon?
That location of that big asteroid, that 2-mile wide, where is it in perspective from our solar system?
So there are several 2-mile wide ones. There are none that we're tracking as potentially hazardous objects right now. But let's see, the one that's half a mile wide, asteroid Itokawa, that I talked about that we got the sample return from, that one is a near-Earth object, but it's not going to hit us. It's not one that we're worried about hitting us. It just sort of follows us in our orbit. The 2-mile wide ones tend to be out in the asteroid belt. There's a bunch of those.
Is it between Jupiter and then Mars?
Yes, between Jupiter and Mars, exactly. Yeah.
Do you worry much about any that come from outside the solar system?
We do. Not necessarily from outside the solar system because those are pretty rare. What we worry about is the Oort Cloud. So you remember from the first slide that I showed when we're zooming in on the solar system, that big cloud of comets, that's almost outside the solar system. And those are the ones we worry about because we don't know where they all are. We haven't mapped the Oort Cloud. We can't see all of that yet. Our telescopes just aren't good enough. And the first satellite to even cross the Oort Cloud was one of the Pioneer spacecraft, and that only happened in the last 10 years. And it doesn't have a camera anymore. All it can do is tell us where it is because it was built long, long ago and it's run out of film. So we don't have a good idea of where all of those objects are. We're still finding things even closer in the Kuiper Belt. That's one of the reasons Pluto got demoted, is because we found something just as big that was in a similar orbit. And oops, now there's 2 of them, and now what do we do?
Have you found any from the Oort Cloud that come in?
We do. Before I was born, it would have been back in the mid-70s, there was Comet Kohoutek that came, and some people here may even remember that it came in. It was discovered 6 months before it passed the Earth. And it was big enough that it would have been smaller than the one that killed the dinosaurs, but it would have been a lot smaller. It would have been a civilization-ending impact if it had hit us. We had 6 months warning. And so when we say we've discovered everything, what scientists will say is we've discovered 99.99% of all of the objects of a certain size. That extra 0.01% that we're saying we haven't discovered, those are Oort Cloud objects that we just don't know about yet. Let's see, in the back?
Cathy, when you talk about things like glitter bombs and nuclear weapons and windsocks deployed in the solar system, et cetera, are you talking about military applications or civilian applications or a joint venture?
That's a good question. Would a deflection or a mitigation operation like this be a military or a civilian or a joint venture operation? So right now, everything is civilian. There is a UN committee on the peaceful uses of outer space that meets about once a year, and they talk about, okay, what are the treaty obligations? What do we need to do to make sure that everyone's involved, that no one country has to take over, that no one country gets blamed if they do it wrong, that no one country has to do everything and shell out all the money. So mostly it is a civilian operation now. If it were an emergency situation and the military could help, they potentially would. However, right now, nuclear weapons in the United States are owned by the civilian Department of Energy, so the military doesn't get to do that. NASA is doing all of the space watch and the telescopes, so they're doing all of the location stuff right now. The Air Force, I believe, has a telescope that helps, but not a lot. So it's the absolute majority of this work being done is being done by civilians. And we meet, as the civilian scientists meet every 3 years to talk about plans for deflection, mitigation, and detection. And then again, the United Nations meets every year to talk about legal and treaty obligations and logistics of getting us all in the same room together and making sure everything works out. So,
I think we have time for one more question.
okay. Yes, sir.
How would a glitter bomb work? Because doesn't the light bulb shaped things need a partial vacuum for the light to make the thing spin?
They work, so the light bulb thing that you saw there works, okay, so you've got one, and I totally breezed over that to speed it up. So, okay, the little light bulb spinny thing, it does need a vacuum, but conveniently for the asteroids, if you're out in space, you already have a vacuum. So when you have the little paddles on the light engine, one of them's, one side is light, one side is dark, so one side heats up, and so you've got photons radiating back off of it after it's heated up. You've got infrared light radiating off, pushing it in the other direction, and that's how it spins, right? So with the glitter bomb, you've got these asteroids that they also spin, and so as they're spinning relative to the sun, then one side of them is warmer than the other because it's just been heated by the sun. So if Bob was the sun here and I'm the asteroid spinning, so as I come past and Bob's rays are heating me up, when I get to about here, my arm pointing that way, that's going to be the hottest point on my surface because the part that's facing him is still getting sunlight. This part's just been heated. Back there, I'm still cold because I'm coming out of the night side. So you've got that same differential in the heating. Now, if you make one side shiny and one side not, then one side will heat up and the other side will stay cold even when the sunlight hits it because it's just reflected. And so then all of a sudden you have a torque on your asteroid where one side is radiating more infrared light, the other side is radiating less, and that yanks on it and pushes it out of the way.
Right, but doesn't it need a partial vacuum?
No, it needs a full vacuum.
Because they've done the tests with the light bulb things, but in full vacuums and it doesn't work.
Really? No, okay, it's a bad analogy then. Okay, I'm sorry. There's enough friction on those things that it doesn't work because you need the gas pushing on it. These things work according to something called the Yarkovsky effect, which is analogous, but does need a full vacuum and has actually been demonstrated on various asteroids that you do get Yarkovsky effect alterations to the spin. But good question, and good on you for holding me to the answer. I like it. Keep that up. Okay.
Let's thank Cathy for a wonderful presentation.
Thank you, everybody. This was really fun.